Good morning. I've got 9 o'clock. I think we'll go ahead and get started. My name is Mike DeLacluse. I'm president of Lesman Instrument Company. I would like to thank all of you for taking time out of your busy schedules to join us for today's webinar, Mechanical Pressure Gauges 101. This training will answer some of the most common questions about mechanical pressure gauges. Our instructor, Jason Deane, will explore the unique role of pressure gauges in plant environments. He will also discuss the basic design principles, the problematic operating conditions that will lead to failure, and what practices you can adopt to improve reliability. The discussion will close with a review of industry trends and how to improve gauge specifications to benefit your bottom line. Jason is a senior instrumentation engineer at WIKA Instruments. He serves as a member of the company's full audit service team. They call their FAST team. Which is a value-added program that provides pressure gauge expertise to plants in the downstream petroleum industry. As a FAST engineer, Jason investigates, diagnoses, and corrects issues with pressure and temperature instrumentation to improve plant safety and operations. Prior to joining WIKA, he worked as a customer reliability engineer and sales engineer for John Crane, where he specialized in failure analysis. He holds a degree in Industrial and Systems Engineering from Virginia Polytech Institute and State University. Because of the large number of attendees, we will be muting the phone lines. If you have a question, please type it into the chat tool so we can respond. With that, Jason, I'll let you take it away.
All right. Thanks very much, Mike. Good morning to everyone. I look forward to sharing some of my insights that I have gained from the last year or so with WIKA and share them with you in hopes of bettering your understanding of gauge use, gauge application, and hopefully helping you improve the reliability of your own gauges in your plants. So without further ado, let's make our way. For today, I'm going to start out by discussing why mechanical pressure gauges are actually important. A lot of people, for them in their plants, these gauges have become a part of the white noise that falls into the background, and they really don't give them the attention they deserve. From there, we'll go through basic gauge design principles. I'll do a discussion of the operating conditions that oftentimes will cause troubles, and I'll discuss the solutions that can help address those problematic operating conditions when they're found. From there, I'm going to take it up a level, and we'll look at the industry as a whole and some of the things that we're seeing in the industry and why maybe gauges aren't getting the attention that they ought to be given. Last, I'll give you a quick explanation of what our FAST services are that we can offer to you as support. And finally, we'll do a summary and a few rounds of questions. So to begin, let's talk about mechanical gauges. Why is it important to maintain them? Mechanical pressure gauges, to begin with, they offer that local pressure indication that you're not going to get in the plant for so many other pieces of equipment that don't belong to the centralized computer systems. They can help you detect signs of degradation in your process performance and other major operating parameters that aren't being tracked in DCS. Oftentimes, they'll help you identify your potential for loss of process or loss of containment. An example there would be rupture discs on large vessels. Additionally, we can help you predict how long a piece of equipment can be safely or economically run through extra data output that you're not going to get through any other form of instrumentation. And finally, they can help you diagnose causes of system and production disruptions. Taken another way, look at the example of a rotating piece of rotating equipment, a small pump. This pump may have one input that's being fed back to the DCS, such as the discharge pressure that it's feeding to a reactor. However, through gauges, you can gather quite a bit more information, such as suction pressure, maybe the differential pressure across a suction strainer, or ancillary equipment such as mechanical seal flushes or steam quenches. All of that type of information comes solely from local indication from these humble little pressure gauges. Slice that another way, and what you've got is that pumps rank first in failure incidents and maintenance costs in plants, and the repairs account for 27% of the life cycle costs of repairs in plants. If you could be doing something as simple as replacing a small little gauge that's going to help you address those failures, you're doing tremendous amounts of work for the reliability of your plant. Now, what we've found in going out and conducting audits of industry plants is that at least 25% of these pressure gauges that are installed in plants require immediate attention. So that means that these gauges are either already failed or are exhibiting signs of imminent failure in the very near future. Additionally, 40% of gauges are exhibiting problematic operating conditions that ought to be addressed by the next maintenance cycle. So that's more than 65% of the gauges in the average plant that need to be addressed in some manner. We'll begin our discussion with the basic principles of design for mechanical pressure gauges. Today, I can't cover all of the different types of gauges that exist in plants, so I'd like to cover the three most popular gauges used in plants, and those are pictured across the top. The board-on-tube process gauge, which is the original technology, a recent technology that's been developed called the direct drive process gauge, and then finally the process gauge in combination with a diaphragm seal, which opens you up to more options as far as process compatibility and addressing problematic operating conditions. Across the bottom, you see a number of other gauges we offer, and if you need more support on any of those, we'd be happy to offer our engineering services to help. So the original design of a mechanical pressure gauge includes these basic features. The pressure connection receives the pressure from the process, and that pressure is fed into the measuring element or board-on-tube. As the board-on-tube is increasing in pressure, the design of the tube causes the tube to actually deflect, and that deflection of the tube is transferred through the pull rod to the movement and ultimately to the rotation of the dial, which reads out the pressure reading on the dial face. These are the basic parts of a mechanical pressure gauge that you don't see behind that dial. The process gauge, which is the first of the three types of gauges I'd like to discuss, is the workhorse of the process industry. These gauges are used throughout, and of course I'm going to speak to the WIKA brand of gauges, but any good process gauge should have similar features as to what's included here. It'll have excellent load cycle stability and shock resistance to handle those rough operating environments in plants. In our case, we include a standard 0.6 millimeter restrictor, which addresses specific failure conditions that I'll discuss later. The case comes with a NEMA 4X or IP65 weather-tight seal, and what that's going to do is it's going to give you a lot of protection from environmental contaminants. There's a standard overload stop to prevent the gauge from overpressurizing beyond the maximum pressure that it's been designed for. Now that doesn't prevent failure necessarily, but it is designed to help, and I'll discuss that more later. All of these cases can be liquid filled, further protecting the gauge's internal moving parts through lubrication and also protection from vibration. And finally, they have a safety case design. What the safety case design means is that this gauge has been designed with a physical wall between the dial face and the measuring element, so that in the event that you have a release of process fluid in your plant, as terrible as that would be, the majority of process fluid will be directed out of the back of the gauge and away from any operator that might be trying to take a reading at the front of the gauge. This is extremely important for hazardous, hot, corrosive chemicals that are being used in plants. So as I discussed, this gauge has been specifically designed for the chemical and petrochemical processing industries, and it's very well suited for corrosive environments and gaseous or liquid media, as long as that media will not obstruct the pressure system. A newer technology that's been born in the last few years is the direct drive gauge. It's ideal for heavy mechanical vibration, high dynamic pulsation, and shock. Inside of the gauge, in lieu of having a board-on-tube with the movement and internal moving parts, it's got, as you see in the bottom right, a coiled, what we call the helicoil, that's made out of Inconel X750. It's highly resistant to temperature extremes. It has excellent oxidation and corrosion properties, and it eliminates that delicate internal movement that so often suffers and ultimately fails. The fact that there's no gears or linkages leads to increased life in really harsh environments. This gauge also includes that safety case design that I discussed previously. Finally, we'll move to the diaphragm seal. The diaphragm seal is another component to be used in conjunction with a mechanical pressure gauge. Either of the two first gauges that I discussed can be used with it. What this does is it now adds a physical barrier between the elements of the pressure gauge and the small cross sections of the pressure gauge, and creates a large, easily flushed or easily maintained environment for the process fluid to operate in. the balance of the system is filled with a system fill fluid that is clean, cooled, and would not crystallize or otherwise obstruct the pressure gauge from operating. This is fantastic to use anywhere that you have process fluids that wouldn't be compatible with the standard materials of a pressure gauge. And of course, if you have any further questions on it, I'll be happy to answer those. So let's move into problematic operating conditions. These are the 8 most common failures, and I'm going to group them into the prevailing failure condition in groups of 2 as we move through the discussion. The first major risk that you have is a risk of board-on-tube rupture. And what we're saying by that is that board-on-tube, due to a overpressure condition, is actually going to burst, much like if you were to pop a balloon. Pressure spike would be one of those conditions. The indicators of a pressure spike would be a bent, broken, or fish-hooked pointer. Sometimes the pointer will have a nick on the side of it where it has contacted with the back of the stop pin. And this is coming from an abrupt, the keyword being abrupt, increase or decrease in pressure. Many times this is caused by a pump being turned on or off very abruptly, or maybe a valve being opened or closed. The board-on-tube would eventually rupture, and you would ultimately lead to a media release. The second type of overpressure board-on-tube rupture condition would be overpressure and high pressure in a steady state. In this case, you'll have a gauge that's got the pointer all the way past the full-scale value of the gauge, and it may even be pressed up against the stop pin on the back side. This is caused when a gauge has been incorrectly specified for a certain application. 30-plus years that these plants have been in existence, many people touching these gauges changing hands. It's very prevalent that people will misapply a gauge just through lack of understanding of the application. And far too often, for example, a 30 psi gauge may be put in where a 300 psi gauge is really required. The risks are the same as with pressure spike. Eventually, that board-on-tube inside of the gauge will reach a point where, as you see on the right-hand side, this is kind of the order of failure. The first thing that happens is you get a little crimp where that red arrow is pointing about around the halfway marker of a board-on-tube. From there, the pressure, as it increases, will eventually transfer down to the end of the board-on-tube, and in the second picture, you can see where that rupture has occurred. And then finally, the third picture shows you both of those conditions in one shot. The way to solve both of these conditions is very similar. First thing you want to do is investigate. Determine what the actual operating conditions for that installation should be. As a best practice, WIKA recommends 2 times normal operating pressure. Now, if you find that there is no way to eliminate or address the overpressure risks, then there's other things you can do with the process gauge and with accessories to address it. For example, our gauge has that overload stop standard that I discussed earlier. Now, that's not going to prevent an overpressure rupture, but it'll at least slow down the effects of overpressure to the point where you can catch it and address it. The liquid case fill is going to reduce internal wear on the gauge, and that's going to lubricate those parts so that they don't wear out and more quickly fail. Finally, in extreme cases, you can use a diaphragm seal with a super restrictor to really slow down the flow of that media and prevent the pressure spikes from being so damaging to the gauge's internals. We also offer snubbers and overpressure protectors if that would help with your specific application. The next type of risk to board-on-tube failure is board-on-tube fatigue. Board-on-tube fatigue is going to be described as anything that will cause the metal wall of the board-on-tube to fatigue, much like if you were to take a paper clip and bend it back and forth numerous times. The first of those failure conditions is pulsation, and pulsation is born out of a fluctuation in process pressure that is causing the pointer to move back and forth very quickly. I hope you can see in the video that the pointer is moving around excessively. I don't know if the video translates well, but in this picture, whatever is happening inside that process line is causing the pointer to fluctuate rapidly from 10 to 15 psi. What happens is that over time, and in this picture you can see, over time, the 2 connecting gears of the movement will wear against each other, and eventually they wear to the point that they're no longer contacting. At that point, the fluctuation of the board-on-tube becomes much more pronounced, and the breakdown of the board-on-tube metal wall is much more accelerated. As that happens, you'll finally get to a point where you have a crack in the thin section of the board-on-tube, as you can see on the picture to the left. The second type of risk to board-on-tube fatigue is vibration. This can be indicated by a missing pointer, oftentimes black dust being all over the dial, or as the dial comes loose, it will scrape against the pointer. Oftentimes you find this around rotating equipment. Misaligned pumps, reciprocating compressors, or anywhere that you have a poor fixture mount for that gauge such that it's receiving vibration from the surrounding equipment. As we discussed, just like pulsation, this eventually will break down your movement. The metal wall of the movement will, the board-on-tube. The metal wall of the board-on-tube will fatigue, and it will lead to a release of media in your plant. In order to address this, you want to begin by investigating and finding out where that vibration is. If it's something that can be addressed, such as a cavitating pump, start there. If not, we have options that we can offer to help you fix those problems. The liquid case fill in this case is extremely important because it's going to lubricate those moving parts and reduce the internal wear and cool those parts as well. In extreme cases of a pulsation, you can use a snubber or even a diaphragm seal with an internal restrictor to really slow down the flow of that media through the gauge and prevent the repeat wear from that dynamic cycling of the movement. Finally, the direct drive gauge, as discussed earlier, is particularly useful in these installations because it's not got all of those moving parts. It's got the one helicoil that is very robust in vibration and pulsation. The next risk to gauge failure would be material deterioration. Corrosion would be the first example, and this is where that seal, that NEMA 4X IP65 case comes in handy. You'll see corrosion through anything from a corroded dial or pointer, build up in the case, a fogged window, or a discolored case fill. This happens when contaminants get inside the case and cause those parts to break down. It may have been caused by a missing fill plug, or maybe the window at some point in time has been cracked, or even the case has been cracked. Eventually what can happen is that that corrosion will reach the board-on-tube and eat away through the board-on-tube, and it could lead to a failure. Similarly, temperature can break down a gauge. The indicators of a temperature failure would be breakdown of the gauge components. Most of the time they'll look like they've been cooked. A discoloration of the dial, or you can even see that the dial face, the window, has been melted to the point that it has extruded out of its original home. This is usually caused by incorrect mounting or incorrect use of accessories. Oftentimes around steam applications or hot applications, the right measures have not been taken to move the gauge away from the temperature source. It's a very long life cycle to failure, but ultimately this can break down the internal moving parts to the point where you could have immediate release. The best way to address issues of material deterioration are to determine what's causing the gauge to break down. From there, our hermetically sealed case will help you with the ingress of contaminants, and the liquid case fill will help protect and cool those internal parts. Now in extreme cases, anything over 212 degrees, we could offer you a diaphragm seal and maybe even a diaphragm seal in conjunction with a cooling tower. In cases for steam, the mini siphon has been found to offer tremendous benefit in lieu of using that instead of a coil siphon or a pigtail siphon. It comes in a much smaller package, and too many times those large coil siphons will get wrapped with insulation either to prevent operators from getting burned, but the problem with that is that that defeats the purpose of the siphon because the cooling effects have been negated. The last category of gauge failure we have is loss of functionality. This is not necessarily going to lead to a release in your plant of any sort, but it can oftentimes be an indicator of gauge maintenance inside your plant. The first cause of loss of functionality would be clogging. Far too often people will look at a gauge and see that it's not working and assume the gauge is broken, when in actuality something has happened to the gauge to prevent it from receiving pressure. The gauge won't show any pressure, and most often this comes from highly viscous, crystallizing, or hardened particles that have gotten into the socket of the gauge and prevented the pressure from reaching the measuring element. Another category of loss of functionality is just general maintenance. Anytime a gauge has been cracked, broken, or missing, you accelerate all of the other forms of gauge failure, such as corrosion. This is just old, neglected gauges, and they, in these cases, if the gauge doesn't need to be there, it should be plugged, or if the gauge does need to be there, it should be replaced. The best way to address these is a standard gauge maintenance plan, and to support a gauge maintenance procedure, we can offer individual parts. Let's say, for example, just a window has been broken. If you leave that window broken out in the field, the ingress of contaminants will eventually break that gauge down to the point where it doesn't operate. But by simply replacing the window, now you've got a completely functional gauge with the hermetical seal that will keep it operating long into the future. Finally, a short discussion of accessories. As I've touched on other slides, we offer a whole host of accessories that can be used in conjunction with your mechanical pressure gauges. Things such as stainless steel tags to help your operators determine what gauge should be installed in what location. This really simplifies the process of installation for an operator when he's out in the field trying to determine what gauge should be installed in a particular location. That mini siphon is going to prevent issues with steam such as water hammer and high temperature, and it's got that small form factor which will help reduce gauge width. Now let's speak about kind of the larger picture industry trends, why gauges aren't getting the attention they really deserve. What we're finding is that in plants, they have considerable unnecessary complexity, and this has taken place from just the proliferation of configurations over the life of the plant. If you think about some of these plants, they predate probably many of us that are on this call. Too often, projects have been done and different engineers have been involved, or things have happened that have introduced more gauge complexity to a plant. If you can work on simplifying the configurations in your plant, you'll reduce the guesswork for operators and installers that are out there trying to maintain these gauges. Things such as manufacturer, gauge type, model, pressure range, wetted materials are all components of a gauge's design that should be considered when trying to simplify the gauges in your plant. Once you've simplified what gauges you're using, you want to develop an effective storeroom inventory that's going to maximize coverage of the installations in your plant, but minimize what you're actually keeping on the shelf. And in doing this, you're going to eliminate that redundant, obsolete, or wasted inventory. Through the audits that we've done in the last year, we've found that you can average about a 75% reduction in the unique configurations that any plant uses. We accomplish this by eliminating those duplicate configurations, by reducing the complexity of those make and model configurations, and standardizing on common pressure ranges that the plant actually uses in their facility. So how did we get here? Why have gauges become such a mess in all of these plants? First, you've got aging infrastructure. As I said, these plants oftentimes are older than us. Numerous projects have been done to re-rate or repurpose existing units, but in many cases, the gauges weren't addressed as part of that project. You may have a gauge that was specified for a previous operating condition that doesn't even hold relevance anymore to the scale that it's now operating under. Additionally, the very people who have come along through these plants who possess the knowledge of gauge application are retiring in record numbers. More than 40% of all oil and gas professionals will retire in the next 10 years. These things compound on each other. The aging infrastructure, those retiring experts, and the brain drain they're taking with them as they retire, and finally the underinvestment into what is actually causing gauge failure. Too many of these plants don't even know what's failing or what to do about it. Any plant trying to address their gauge functionality and improve reliability and total operating costs should have some main objectives in mind. First objective would be to reduce their complexity and to standardize. The result will be that they eliminate the misapplication and repeat failures of gauges that are occurring out in those fields. Just by getting the correct configurations on their shelf, they're going to prevent that short life cycle that so many gauges fall victim to when they haven't been installed in the correct application. Next, specifying those correct conditions is going to improve reliability so that when the gauge can actually handle the operating conditions, it's now functional again, and the operators will have a drive to actually use the gauge rather than assume that it's just broken. And finally, if the gauge is actually functional, now your operators have the ability to troubleshoot that larger, more expensive equipment. They can use it for troubleshooting, and they can do predictive maintenance just by virtue of the fact that they have those functional gauges installed. As I said, I'm a part of the FAST Services team. We offer a host of services that we can provide to you. The cornerstone would be the instrument audit, where we will actually come into your plant and review all of the gauge installations you've got to compare them to either a plant specification or industry best practices. We can also tailor one of those audits to a turnaround that you've got and help you coordinate the logistics and timing of delivery of product to make sure that the gauges that you need are delivered when you're ready to install them. On an ongoing basis, we can offer instrument failure analysis. Anytime you have a gauge maybe that's giving you repeat failure, we'd be happy to have you send it in to us. We'll review it, discuss the operating conditions where it's installed, and try to help you find a long-term solution for that installation. Last but not least, we've got instrument safety training. I could offer this type of package to you or your operators in your plant as needed, and we'd be happy to help. So that's the presentation I have for you today. If anyone has any questions, I'd be happy to answer them. I did have one question request on the internet, and this comes from Richard, and he'd like to know, how can I protect low pressure gauges, the diaphragm type, from overpressure damage in an academic lab setting? The answer to that, Richard, is that our pressure gauges, and let me try switching here, see if this works. If I'm not mistaken, the diaphragm type pressure gauge you refer to is something like this. Now, this gauge is designed standard to be able to handle 5 times full scale value, as you can see right here for the overpressure safety. Additionally, we can work with you on the design of the seal to actually make the upper housing match the profile of the diaphragm seal. And in doing so, we can actually step that pressure safety rating up to 10 times the full scale value of the gauge. You would just need to inquire with us, and we'd work out with you on the design, and we could get that out to you.
Jason, I have other questions, so when you're ready for them, let me know.
I am ready for the questions.
All right. I'm hoping you can pull this up either off your website or have it on your computer there. The question is a diaphragm seal in conjunction with a cooling tower. Did I hear that correctly? And basically, I think the question is, in applications of hot media, sometimes you've got to put something in between the diaphragm seal and the gauge to dissipate enough heat.
That's correct. And yes, we can do that. And
then he says, could you please elaborate on what a cooling tower in this instant means?
Sure.
So do you have a picture that you can pull up of a WIKA cooling tower? Because there's some confusion between what WIKA means by a cooling tower and what some of our customers might mean by a cooling tower.
I would be happy to do that for you. Let me, I don't know if it's going to be on this page or in accessories, but I can certainly show you what a cooling tower looks like. Let's see here. Here we go, diaphragm seal assembly with cooling tower. So as you can see right here, what we have is a Excel process gauge, and this right here is a 4-inch cooling tower. We offer that cooling tower in 4, 6, and 8-inch applications, and we can actually work with you. We've done the research to determine what the cooling effects of those different cooling towers would be for various process media, and we'd be happy to share that. But this is what I was speaking about. You've got the diaphragm seal located at the bottom of the assembly, and actually we put the cooling tower inside of the system fill. And what that will allow us to do is the cooling tower remains part of the clean system fill environment, So it's not exposed to whatever the process fluids are, whether they're corrosive or clogging in nature. And there's a very thin drill through that goes through the center of that cooling element. And by creating a small cross-section of fluid and adding those fins on the cooling element, it allows us to greatly reduce the temperature by the time it reaches the gauge. Also, if there's extreme temperature issues, we can actually install a diaphragm seal to a capillary assembly, and you can remote mount your gauge much further away from the heat and prevent it that way as well.
Any ideas to what sort of temperatures you can get away with mounting that seal in?
Let's see here.
Really be dependent on the fill fluid, right?
It's gonna the fill fluid is that system fill will be part of the limitation on temperature and also the size of the cooling element. So in this case, the standard 4-inch will dissipate up to 300 F, and if I'm not mistaken, I would have to check for you. We can get configurations up to 400 and I think even 500 degrees Fahrenheit with the standard cooling element. I think 500 becomes the limitation where you'd then want to go to this diaphragm or the capillary assembly, such as you see here. But if the person asking the question would like to contact me, I'd be happy to research it.
Yeah, I think the person that's asking the question, I've got his name. We'll have to contact him to go over that application specifically because he's talking about 500 to 600 degrees, I think. So
okay, we can definitely help. I would want to put that through our engineering department.
Exactly. All right. The next question is: are the fluids that are used in gauges, in other words, to fill gauges, are they treated with an antifreeze, or does that have to be specified? So, you know, when we talk about glycerin, any ideas to what sort of, you know, typical glycerin can go down to? And then maybe you should talk about the other fill fluids that we can put in gauges for dampening, like silicone, to see if they can get down to lower temperatures.
Here's a list of the standard fill fluids that we'll use either in the system fill or in that liquid case fill. Glycerin would be our standard recommendation for a liquid case fill, and boy, you're gonna test my knowledge right now.
Yeah, we're going to have to look up. There's actually a chart,
yeah,
I think, that shows you what the temperatures are. And
there is, and I've got it, just not handy. I'd be happy to even send that out if the person would want to give me their contact information.
I've got it.
Glycerin does have antifreeze capabilities, so it would be able to go down pretty low in temperature.
Yeah, in most applications, at least outdoor applications around here, glycerin's fine. Because when you mix glycerin with water, it'll take a fairly low temperature. But we're going to have to find that chart that gives us the temperature ratings for each fill fluid and get that to this customer. Yeah. So we'll go ahead and do that after this session. I think we'll also post it along with the session so that anybody watching it can look it up right there.
Okay. We may. Let's see here.
Then the next question is, do you have any best practices for pressure gauges on moist gas lines in cold weather applications?
Okay, sorry. Let me just real quick. Here's your temperature ranges right here.
Yep.
Sorry, not to take you out of order. We just found them.
Yeah, that's okay.
So for glycerin, you can go for the 99% glycerin, which is the standard one that we recommend. You can go -20 Celsius up to 60 Celsius. And I'd have to convert that for you to Fahrenheit, but that can be found on our frequently asked.
Yeah, it's -4. It's,
oh, yeah, there we go, right above. We don't have the F by it. And this can be found on WIKA's website in the frequently asked questions section.
You know, there you're showing 99.7% pure organic glycerin. When you cut it with water, I think that temperature actually goes down a little.
Okay.
It's one of the anomalies.
I can look into that for you.
Yeah, I think we'll have to look that up because typically I think you guys cut it with like 12% water to bring that freezing point down.
To dilute it down a little bit. Okay.
All
right.
Again, back to the next question. Do you have any best practices for pressure gauges in moist gas lines in cold weather applications? That's a tough one.
Moist gas lines in cold weather applications. Is the concern there condensation?
I'm sure it is. And the freezing moisture.
And the freezing moisture in the lines. Well, from a instrument longevity standpoint, that sounds like a perfect opportunity to separate the pressure gauge sensing element from the actual process fluids. I would say that putting in a diaphragm seal that would give you a much larger surface area for the diaphragm to interact with the media would prevent any of that, the freezing of the moisture in the lines from affecting the measuring element. If the issue at hand is something different than that, I'd be happy to research it more,
yeah,
but I anticipate that's probably what the question is.
Yeah, no, I agree with your answer. I think the best way to do it would be to put a diaphragm seal in and separate that moisture out.
Yeah.
Keep it in the process. Next question is, what would be a good application for a low pressure, high oil temperature setting? He's saying between 500 and 600 degrees. So now we're really into an application we're going to have to think through and engineer.
Yeah, I would. My gut would tell me that it would be a diaphragm seal connected to a capillary to locate the gauge far enough away that it wouldn't be affected by the high temperature. And then for low pressure, that would mean that we're either using a seal gauge or a low pressure capsule gauge. And I would just need to make sure that it could handle that kind of installation.
Yeah,
it would probably be the combination of the two, though.
Yeah, you'd also have to make sure that the diaphragm that's just select has enough displacement to handle the low pressure gauge. So
yeah, it would probably be a very large diaphragm.
Yeah, there are some intricacies there that would have to be worked through to make sure that application worked, but it can be done. Mm-hmm. So again, I've got the customer's name. We can get in touch with him on that exact application. Next question, can you explain about pressure gauges with a pigtail? Any advantages or disadvantages? The pigtail being the pigtail siphon. This is the original siphon technology. The newer technology being that short mini siphon that I referred to in the presentation. The pigtail siphon and any siphon really must be installed correctly in steam or process applications. What the point of that siphon is to introduce a volume of liquid media. I'm going to use steam as the example since it makes the most sense. You should put a volume of water inside of that pigtail before installing the gauge, and that's going to separate your gauge from the steam. Now that serves two purposes. Number one, it's going to cool the hot steam before it reaches the pressure gauge, and the airspace above that liquid volume inside of the pigtail will dissipate the temperature. And number two, it also prevents water hammer, which is very prevalent in steam applications, from actually reaching the gauge and damaging the gauge from pressure spike. So that is what the pigtail siphon is intended to do. The problem with the pigtail siphon is that, number one, it's a very tall assembly, and when it's installed around vibrating equipment, it will induce gauge whip on the gauge and lead to accelerated failure that way. Number two, and I discussed this in the presentation, far too often these pigtail siphons get wrapped in insulation, and that completely negates the cooling effects of the siphon, which is why it's been installed there. The solution is the mini siphon. Its smaller package reduces the need to wrap it to prevent operator contact, and it gets used in the same way by creating an airspace above or below the gauge and above process to prevent temperature and pressure spike. It's a great option, and we've had tremendous success with that where it's been used. Good answer. The other question I had very early on is, where can I download the slides? We're going to put this recorded out on our website. We'll send out a message that lets everybody know that it's posted so that they can see it. We'll also pull up these temperature charts and make sure that we post that with the presentation as well. So at this point, I don't have any further questions. Jason, I want to thank you very much for your presentation. If there are any other specific application questions or anybody would like to discuss having a fast safety audit for their facility, please give us a call at 800-9-LESMAN or 800-953-7626. If you're not sure who your account manager is, feel free to ask for me, Mike DeLacluse, and I'll make sure that you get taken care of. We are planning another webinar in mid to late March. The topic is going to be how to select the best non-contact level technology for your application. Please watch your email for an invitation. At this point, I've got no further questions, so our presentation will conclude. Again, Jason, thank you.